Let's talk now about numeric differentiation. So we're distinguishing numeric differentiation from symbolic differentiation. So symbolic differentiation is where we have, something like f of x equals, 3x squared plus 2, and we say f prime of x equals 6x. Okay. Numeric differentiation instead takes advantage of the definition of the derivative. So basically looking at the slope at a certain point. So if we look at 3x squared plus 2, it looks something like this. And we can then look at, so the derivative is the slope with the tangent. We can look at the secant, which is, let's say, the slope between two near points. So we can look at, let's say, f of x plus, f of x plus some epsilon minus f of x divided by epsilon. That is going to give the slope of this line. So basically, we take the f of x plus epsilon minus f of x, and that will give us the rise, and then the difference is epsilon, and that's the run. So that gives us the slope. So just for an example here, let's say we were trying to evaluate f prime of 3. According to our symbolic differentiation, that should be 18. If we look instead at this numeric differentiation, we can look at f of 3 plus epsilon. Let's just say epsilon is fairly large right now, 0.1. Often you'll use very small epsilons, like 10 to the negative fifth or something, but let's just do this number because it may be easier to calculate. Minus f of 3 over 0.1. Well, what's that equal? That's equal to 3 times 3.1 squared plus 2 minus, so 3 squared is 9 times 3 is 27, a total of 29. And this is all going to be over 0.1. And let's just figure. So 3.1 squared is going to be around, let's see, 3 times 3 squared minus 2 times 3 times 0.1. So 2 times 3 times 0.1 is going to be minus plus 0.6 plus 0.1 squared, so 0.01. Plus 2 minus 29 over 0.1. And this, moving on over here, is going to be equal to, well, let's see, 3 times 3 squared is going to be, again, 27 plus 2 is 29. So this 29 is going to cancel with this and this and this, and that's going to just leave us with 3 times 0.61 over 0.1. What's that going to be equal? That's going to be equal 1.83 over 0.1, which is 18.3. So we can see this is our numerical approximation to our derivative, and this is our actual derivative. If we had decreased epsilon, right, so this was for epsilon equals 0.1. As we decreased epsilon, we would have gotten closer and closer to 18. And that kind of makes sense, because basically the limit as epsilon approaches 0 of this value is in fact the derivative. So as epsilon gets smaller and smaller. So why do we care about this numeric differentiation? Well, we're going to be calculating some derivatives in terms of gradients. And numeric differentiation gives us a nice check on whether we've got the calculation of those derivatives correct. As you're doing gradient descent, you may be using a package like PyTorch or TensorFlow, which knows how to do automatic gradient calculation. Right? So basically, it's computing the symbolic derivative. However, if you are doing something by hand, where you are calculating the gradient and writing the code to do that, it's worth doing this check. And basically the idea is you calculate the gradient, right? Where the gradient is going to be some array of partial derivatives, right? Where we're looking at the loss with respect, let's say, to theta 1, the loss with respect to theta 2, all the way to the last parameter. Okay, so this we're going to calculate symbolically, let's say. So we'll use our machinery that knows, for instance, the derivative of f of x minus y squared is 2 times f of x minus y times the derivative of f of x, something like that. So we may be using the chain rule fairly long, and so we're going to get our values here. What makes a lot of sense to do is double check these gradients. Okay, once you've got the machinery working, you don't need to keep rechecking it. But when you've first written a code in order to calculate gradients, it's definitely worth double checking that gradient code. Because if your gradients aren't being calculated correctly, then for sure your gradient descent isn't going to be working, right? You may think you're doing gradient descent and you're actually walking up the mountain or, some random direction. So it's important to do that. So basically the idea is go through and double check. How do you double check? Well, basically you're going to take L, okay, calculated using theta sub 1, whatever the current value of theta sub 1 is. And then you're going to also calculate the loss of theta sub 1 plus epsilon. Okay. So basically, you calculate the loss as you normally do, and then you also just tweak theta 1 a little bit and calculate the loss. Subtract these two, divide by epsilon. This should equal this value, roughly. Similarly, we do the same thing for theta 2 to theta n, and this verifies, yep, we are calculating all these gradients correctly. Then you no longer have to do this calculation because you have verified that your symbolic gradient descent calculation is working properly. But I got to tell you, as I know, if you're writing stuff from scratch, it can be very frustrating to find that, oh, actually my gradients are not quite right.